Hello, I'm Eric Blais from the University of Waterloo. Today I'll be talking about joint work with Shalev Ben David on composition theorems for randomized query complexity. Our main object of study today is a randomized algorithm. A randomized algorithm has access to some input x, and it also has access to some random bits that it can use to randomize its decisions. The algorithms we'll be looking at are computing partial functions. A partial function is a function where for some inputs, the value that we denote for it is star, which just means don't care or undefined. Or another way to think about this is that our partial function is only defined on a subset of the input, and it's perfectly fine to just think of the model in which the algorithm is promised that any input that it is given comes from this set of inputs on which the function is defined. Now we say that a randomized algorithm computes a partial function f with bounded error if for every input x for which f of x is defined, a will output the value of f of x with probability at least 2/3. And what we'll be really interested in today is the query complexity of a. So in this model, a does not get all of x, instead it gets an oracle access to x where it can ask for any of the bits of x. And the query complexity of A is the maximum number of index of x that it needs to query before it terminates during its execution. And this gives us a very natural measure of the complexity of x, where R of f is the minimum query complexity of any algorithm A that computes f with bounded error. There are many variants of this model. One of the variants that will show up later in this talk is the small bias randomized query complexity of functions. And here we say that A computes f with bias gamma, for think of gamma as being a very small value, if for every x on which f is defined, A outputs the value f of x with probability at least 1/2 plus gamma. And now this gives us different values of the randomized complexity of f at different bias levels. We'll study this later on, but for now, let's go back to just the bounded error model, where we think of the algorithm A having to compute f of x correctly with probability at least 2/3 on every input. So before we continue, I also just want to point out that if this sounds very similar to the randomized decision tree model, in fact, this is not a coincidence, the two models are exactly equivalent. So what we are really looking at here, R of f is the minimum depth of any randomized decision tree that computes f with bounded error. So once we have this measure R of f, there's many basic questions we can ask about it. And one of the most basic questions we can ask is how does this complexity measure behave when we apply basic operators on the functions? For example, we can ask what happens to query complexity when we take the composition of functions. Here, the composition of functions f and g is just the value of f when each of its inputs is actually the output of g on some different inputs. Now, function composition has been studied extensively over the years, and for query complexity, we have that indeed in the deterministic model, what you would expect the behavior of query complexity to be is exactly what happens. Namely, the query complexity of f composed with g is exactly the product of the query complexity of f times the query complexity of g. And also in the quantum query complexity model, the same is true. Asymptotically, composition just turns into the product of the query complexities. This leads us to our main conjecture that the same is also true for randomized query complexity. Now, the upper bound in the conjecture actually follows from standard arguments. And also, if we replace f with the identity function, we obtain some very well understood problems such as the direct sum and the direct problems. And even for specific functions f, such as the parity function, we also have quite a good understanding of these special cases of the composition conjecture. But then the main question is, how close to tight is this upper bound for arbitrary f and g. Now, the state of the art on this problem is far from being tight. What we know is that for any total or partial functions f and g, the randomized query complexity of their composition is at most the query complexity of f, r of f, times the square root of r of g. And if we replace one or the other of those randomized query complexities with other complexity measures on f or of g, we can also get different results. Such as, for example, we do know that the query complexity of the composed function is at least the sensitivity of f times the randomized query complexity of g, and there's other variants and strengthenings of these results that are known. But we also know that there's a variant of the conjecture which is very much false. Specifically, Gavinsky, Lee, Santha, and Senyal showed that if we consider partial functions g and relations f, where relation is a generalization of a function where for every input you could potentially have more than one valid output. In this case, with this slight generalization, the composition conjecture is actually very false. So there are relations f and partial functions g, where the query complexity of f composed with g is r of f times only the square root of r of g. And what this counterexample shows is that one of two things must be the case. Either the composition conjecture for randomized query complexity does not hold when f is a partial function either, or if it does hold, it must be because there is some argument to establish this conjecture which actually uses the fact that f is a function and does not generalize to relations. In the Karen paper, we give three main new results on the randomized composition conjecture. And the first one says that actually it does not hold, so the first of the two cases in the last slide is the case. Namely, we can actually find partial functions f and g such that r of f composed with g is polynomial factor smaller than r of f times r of g. And there's different ways that we can express the relation between r of f and r of g and the different powers we could put in there. But there's one thing that this statement of the theorem does not show, which is important to mention. It's that the functions f in these counterexamples have very small query complexity. So this means that if we allow n to show up on the right-hand side of the equation, the counterexamples that we have do not rule out a slight weakening of the composition conjecture. It still allows for the possibility that the query complexity of f composed with g is at least r of f times r of g just divided by log n. This limitation of the counterexample to us kind of suggests that it's actually still worth trying to prove the strongest possible composition theorem that we can have for randomized query complexity. Our second main result will show that actually the composition conjecture does hold if we introduce the notion of noisy query complexity. Noisy query complexity is a variation of the standard query complexity model where now we want to give the algorithm or the entity that is querying the oracle a little bit more control over those queries. Specifically here, we're going to say that if you have a noisy oracle for x, you can query any bit I of x, but you can also specify a bias parameter gamma. And what the noisy oracle does is that it will return a random bit which is biased towards the value of x sub I. So it will return a bit which equals the ith bit of x with probability 1 plus gamma over 2. And since this gives us less information about this bit, it's natural to actually also modify the cost to reflect this. And so we'll say that the cost of a query with bias gamma is gamma squared. And as before, we can now compute the query cost of an algorithm using this noisy oracle. And then once we have this noisy query complexity model, we can define the noisy randomized query complexity of f, noisy r of f, to be the minimum cost of an algorithm that computes f with bounded error when accessing the noisy oracle. So with this model in place, what we can show is that for every partial function f and g, the query complexity of f and g is at least as large as the noisy randomized query complexity of f times the standard randomized query complexity of g. And here it turns out this is the strongest result possible in the following sense. For any other complexity measure that you would have, where you can show that for every partial function f and g, the query complexity of f composed with g is at least m of f times the query complexity of g, all of those complexity measures must be bounded above by noisy r of f. And then finally, our third result shows that if we actually consider the non-adaptive query model, where an algorithm must decide all the bits of the input x that it wants to query before observing the value of x on any of those bits, in this non-adaptive model, the strong version, the original version of the composition conjecture does hold. So the non-adaptive randomized query complexity of f composed with g is equal to the non-adaptive query complexity of f times the non-adaptive query complexity of g. In the rest of the talk, I'll give a brief overview of the main ideas behind the proofs of those three theorems. Let's start with Theorem 1. This theorem gave the counterexample to the original formulation of the composition conjecture. And the proof is actually similar to the proof for the case where f was a relation. And here, at a high level, what we really want to do is we want to find a partial function f where the noisy randomized query complexity of f is much smaller than its regular randomized query complexity. And we want to identify a function g which can be computed much more easily to small bias than to bounded error. Once we have those two functions, we can actually complete the proof quite easily just by simulating the noisy oracle for f using the small bias algorithm for g that's very efficient to actually then obtain an algorithm that computes f composed with g and which has cost which is much less than r of f times r of g. So the main requirements of this proof is really choosing those two functions, finding those two functions f and g that satisfy those two requirements. Now here I will oversimplify slightly, so the parameters I will be giving you are not the correct ones, but conceptually these are the ideas that give us the right functions. So first, which is a function that has very small noisy r value? And this function is the approximate index function based on the usual index function. The standard index function, we can think of it as having its input be split up into two parts, the address A and the rest of the bit string that we're calling x here. And the value of the index on input AX is just the value of the bit of x at the index given by the address A, so x sub A. For the approximate index function, we actually design a partial function that makes it easier to compute. And the way we do this is by saying that actually the function is only defined on inputs where all the bits of x whose indices are very close to the addressed index have the same value as that addressed index. And just for the simplicity, let's think of the rest of the inputs being undefined, actually being stars. So any bit of x for an index that's far from A will actually be undefined. And what we find with this function is that if we have access to a noisy oracle, we can actually compute it very easily by just getting slight bias approximations of the first of each of the address bits, and using this to get an address B which will be close to the address A, and then by querying this value of x at the address B, this will give us the value of the function. On the other hand, if we do not have access to a noisy oracle, the best we can do is to query the entire address and then the corresponding bit, which has much higher cost than what we had with the noisy oracle. Okay, so this gives us the function f that we needed. The last thing we need to do to complete the proof that we gave as an overview earlier is to actually find a function g, which is much easier to compute to small bias than to bounded error. And here we can take the standard gap majority function. We take the usual majority function along with the promise that the only inputs we will be given are inputs that are far from being balanced, inputs where there's quite a few more ones than zeros or vice versa. And here, just choosing the size of the gap appropriately gives us a function where, to small bias, we can compute it with a single bit by just choosing a bit at random and outputting its value, but where for the bounded error case, we actually have to compute a linear number of the bits of x in order to succeed with the required bounded error. So then, as mentioned in the overview, once we have this f and this g, or more precisely some slight variance of those functions, we can plug them in together to complete the proof of our counterexample. Okay, so now onward to the proof of Theorem 2. Theorem 2, you'll recall, states that the randomized query complexity of f composed with g is bounded below by the noisy randomized query complexity of f times the randomized query complexity of g. The idea of the proof is to apply a standard simulation argument. So if we let A be an algorithm that computes the composition f composed with g very efficiently, we just want to design an algorithm B that computes f by itself by simulating A using the noisy oracle to replace the inner function g. And we want to do this in a way that we can argue that the cost of B is bounded above by the query cost of A divided by R of G. There are two main ingredients in the proof. The first key ingredient is a Minimax-Like Result. Specifically, we can show that for every non-constant partial function g, we can find two distributions, mu0, which has support over the 0 values of g, and mu1 supported on the 1 values of g, such that for any query algorithm A, we have that the Hallinger distance between the transcript of A on mu0 and on mu1, where you can think of the transcript as just the values of the input that were revealed by the algorithm. If you look at the distribution of the values of the bits revealed by the algorithm under mu0 and mu1, the distance of those two distributions is at most the query cost of A over R of G. And the reason I call this a minimax-like result is because actually if we rearrange this inequality, we can see that it's equivalent to saying that R of G is bounded above by some cost of A over some notion of score, of discriminating score over some fixed distribution by A. And the proof of this result does not follow from standard minimax theorems, but it does follow from the new minimax theorem that we introduce in the companion paper, for which you can see a separate talk. And the reason the ingredient 1 is useful is because we can actually connect the cost of simulating an oracle to G to this Hallinger distance between two distributions. Here I can give you the toy version of this simulator where we only query a single bit. In this toy version of the problem, we let mu0 and mu1 be two known distributions over a single bit. But we let B be a bit that is not known and that we can access only via the noisy oracle. Then the second main ingredient of our proof is that there is a protocol where the output value of this protocol will be distributed exactly according to mu sub B, even if we don't learn B exactly. And the expected cost of the protocol is exactly this Hallinger distance between the two distributions mu0 and mu1. And actually, the protocol itself is quite simple. So just to simplify the presentation, if we think of P0 and P1 as being the probabilities that we output 1 under mu0 and mu1 respectively, and we assume that P0 plus P1 is at most 1, then what the simulator does is with probability P0 plus P1, it calls the noisy oracle with an appropriate bias parameter, and otherwise it just returns 0. And if we actually just complete the analysis of this simple simulator, we see that it does satisfy the conditions of the lemma. And then once we have this simple simulator, we can actually build upon this to actually build the complete Oracle simulator, which does let us actually simulate the algorithm A on the composed functions f composed with g with the appropriate cost, and complete the proof of our second theorem. And finally, let us see the proof of the theorem 3. This theorem states that in the non-adaptive setting, composition does correspond to multiplication of randomized query complexity. And to prove this theorem, what we actually want to show is that the non-adaptive noisy randomized query complexity of f is asymptotically the same as the standard non-adaptive randomized query complexity. We can actually do this by connecting the problem to some known results in the analysis of noisy channels. And once we have this connection, we can apply a result of Samorodnitsky and Polyansky and Wu, which states that for any function f, any distribution mu on the domain of f, and any parameter rho, if we look at the conditional entropy of f of x, conditioned on either having a noisy version of x, where we apply noise, where we flip the bits of x with some parameter rho, and we look at the conditional entropy from an erasure channel, where instead we erase each bit of x except with probability rho squared. In fact, the conditional entropy is larger in the noisy setting. And so this lets us actually convert a noisy oracle to x, to the input x, into a different model where we would, instead of applying noise to the answers that we return to the entity querying the oracle, we would actually erase the values that we return with some probability, which we can then turn into a standard oracle. And doing this, we can actually establish what we wanted to show, that having a noisy oracle gives you no extra power in the non-adaptive setting. So this concludes the proofs of the 3 theorems that I wanted to cover in this talk. I just want to leave you with the strongest form of the composition conjecture that still remains open today and possible. So this strong version states that for every functions f and g, the composed function f composed with g has query complexity at least r of f times r of g divided by log n. Our results show that this composition conjecture is exactly equivalent to different ones stating that for every partial function f, noisy r of f must be at least as large as r of f divided by log n. And in fact, in the paper, we give a characterization of noisy r of f in terms of composition with the gap majority function. So both the composition and the noisy query complexity conjecture are equivalent to a conjecture which just states that for every function f, r of f composed with gap majority must be at least as large as r of f times n over log n. Establishing or disproving any of these conjectures would actually settle all 3 of them. And that's it. Thank you very much for your time.